In this video, I'm going to be working problem 2.5 from Classical Mechanics with MATLAB Applications by Javier E. Hasbun. This problem says we should use equation 2.412, which I'll write down in a second, to obtain position as a function of time for an object falling. And you should know from basic physics that our force in this situation is going to be F equals negative mg, where I'm representing down as negative. Now, the book says to use one particular equation, so let me put that up. So this is the equation the book tells us to use, and I'm just finishing up here by replacing my d in the integral, my differential, with a prime, just because it bothers me that the upper limit of the integral is the same as the thing I'm integrating with respect to. I get what they're going for. They're both positions, but one is like a tiny little bit of position, and one is considered a final or the upper limit of the integration. So I'm just going to use t prime and x prime in the actual integration instead of x and t. It doesn't change the math or the physics in any way. It's just more of a notational nicety that I prefer. So hopefully you realize from the physics of this situation what the total energy is, because if you look in this equation, we're going to use the total energy minus the potential energy. And so hopefully you recognize that the total energy, if we start this thing from rest, is just the initial potential energy it had when it started falling. So mgy naught, its initial position. And the potential energy it has at any moment would just be mg in our current y. So I need to substitute mgy naught and mgy into those places. Let's see what I end up with. If I fill in that information, here is what I have, this equation for t. And all I've done is filled in the physics bit. I needed to know what the energy was initially and what the potential energy is as a function of position. And notice I switched from x to y and moved the mass under the square root onto the top just for the sake of space. So this equation reduces if we move the variables around a little bit. So I'm just going to pull out the things not actually involved in the integration. So what I've done here is just pulled out all of the constants, and notice that I factored out a y naught in the bottom, even though there wasn't one on this side, so that means I divide by y naught, and that results in the equation looking like this. Now I'm running out of space, so I'm going to need to flip to a clean page. So if you are following along, you may want to write down this line. And that got a little sloppy. This is a 1 right here. So you may want to write down this line before I move on, and I'll just give you a second to do that. Okay, so I've carried out the integral from that last page, and if you're confused or feel like that was too fast to move, just going from that last line to actually doing the integral, in your textbook, examples 2.3 and 2.4 walk you through the integration that I just kind of glossed over there. It's a U substitution. Or at least they walk you through a version of it that you can see in a similar problem. So if you're confused about the mathematics behind that, look at examples 2.3 and 2.4 in the textbook for the class. Finally, now that I have this equation for t with some algebra, you can solve for y. And again, that is just algebra, which I'm going to assume you can do. And I get, quite unexpectedly, if you remember from kinematics and basic physics, all we had is acceleration. We had no initial velocity, so this is y equals initial position minus 1/2 gt squared. The minus because we've called gravity negative. And that's it. That's how you solve this problem. Handily, equation 2.412 does a lot of the work for you. I don't think you should try to memorize things in general. But hopefully you'll practice that equation enough in this class that it would be, you at least know where to look for it. That should be your minimum level of knowledge is, oh, this is the kind of question that I can answer with that integral dt changing to integral over dx equation. And really it comes out of the definition of velocity. So where it all comes from is that we can go from x to the first derivative of x using Newton's notation is square root 2 e minus v of x over m. All coming out of the definition of total energy, which is V naught plus T naught equals total energy, or defined to be total mechanical energy.